Good morning, everyone. Welcome to Nano Open Webinar. We have Steve Beeby from University of Southampton today. Professor Beeby is one of our TeamNANO researchers. He will talk about electronic textiles engineering towards invisible and ubiquitous wearable technologies. Before Professor Beeby starts his presentation, I would like to give you a brief introduction about him. Professor Steve Beeby holds a prestigious Royal Academy of Engineering chair in Emerging Technologies on e-textile engineering. He received his Bachelor of Engineering degree in Mechanical Engineering from University of Portsmouth. And he completed his PhD studies in MEMS resonance sensors at the University of Southampton. He currently works as a professor at the University of Southampton since 2011. His research interests include the application of flexible electronics, smart printable materials, and energy harvesting technologies to electronic textiles. He is a fellow of IEEE, IET, and IoP. Welcome, Steve. The floor is yours.
Great. Thank you very much for the kind introduction, and good morning, everybody. So I'll just share my screen. Hopefully this will work. Okay, hopefully you can see the screen. Is that okay?
Yes, it's okay.
Okay, great. Thank you. Yeah, so today I'm going to give you quite a high-level overview of the work that we do in Southampton on the topic of electronic textiles. And in particular, I'll explain the vision and what we're working towards as we go along. But it really is about putting electronic functionality in a wide variety of forms into a otherwise normal fabric or textile. So yeah, the talk will just cover the vision and objectives, what we're trying to achieve, and then I'll give you a sort of high-level overview of our activities in energy harvesting and wireless power transfer, energy storage, some of the manufacturing methods we've developed to fabricate these e-textiles, and finally some example applications to try and bring it to life. So the vision, so basically, as I said, so e-textiles, electronic textiles, e-textiles are otherwise standard fabrics that have electronic functionality, be it circuits, sensors, maybe energy storage, batteries, supercapacitors, wireless telecommunications, all these sorts of functionalities embedded within the textile. And traditionally, this has been quite a sort of hobbyist approach where people have sort of taken conductive wire and sewn it into a textile and connected rigid PCBs, etc. And what we're trying to do is get away with all the wires, remove all these sorts of manual processes, and invisibly integrate the electronic functionality, so the sensors, the electronics, the energy storage within the textile. Batteries, as we'll see, are a real problem for the technology. They're obviously they go against the sort of nature of a textile. So we're also trying to remove the reliance on batteries. So the vision really is that you can engage with your wearable technology simply by getting dressed in the morning. So you simply get dressed, and you, for example, your clothing has a lot of the functionality a smartwatch might have. And also we're trying to design the technology in such a way that the user has minimal intervention required. For example, recharging or changing a battery. If we can get rid of that as far as possible as well, that would be a great thing. This is really challenging because this means the electronics has to survive the same conditions, the same use environment that the textile survives. And textiles are incredible materials. They're very strong, very flexible, have unique sort of mechanical properties, etc. And yeah, the electronics has to survive that and indeed survive things like machine washing, which is a very robust environment. So I mentioned batteries are a problem. So at the moment, if you want to, if all e-textile systems are powered by batteries, and if you are making a sort of e-textile system, then you sort of search on the internet for e-textile batteries, then you get these sorts of standard offerings on the left-hand side, which are really impractical. So any commercial e-textile garment will have the batteries basically in a plastic rigid box that will sit in a pocket in the garment. And if you've got this box, then you might as well put as much electronics in the box as possible as well. And that means the e-textile itself has very, very limited functionality, typically electrodes for sensing ECG. Or in the case of this example here, they have actually incorporated some inertial measurement units, so IMUs, that monitor the movement of the individual. Now, in this case, this is a commercial product that's been developed for people playing golf. So there's lots of sensors located around the bodysuit, and that tracks the golfer's motion and enables the coach to look at the swing in great detail and analyze the player's performance. So this costs over $5,000 plus an annual renewal for the software. And these sensors are rigid. You can see the wires here, etc. So these have to be removed. Everything has to be removed. There's a big battery pack. Everything has to be removed before washing. So it's not a particularly practical, or the technology is not very well hidden at all within that garment. And another example here is the Tesla suit, which is similar. It has IMUs as well, but it also has electrodes for providing haptic feedback. So this is potentially for things like virtual reality applications. This costs over $10,000 for a suit like this. Again, needs a big, large battery power pack for it to function. So again, we're trying to make this sort of achieve this sort of functionality, but in otherwise normal-looking clothing. So first thing then is removing the reliance on batteries. So energy harvesting is an obvious approach that we've investigated. And what I'm going to show here is a textile triboelectric generator. So this harvests mechanical motion, converts that into electrical energy. Now, triboelectricity you're probably familiar with. If you take a balloon and you rub it against your jumper, the surface of the balloon becomes charged, and you can see that you can show that visibly here with the baby's hair being attracted towards the balloon. And it's the same triboelectric mechanism that makes a Van der Graaf generator work as well. So in this case, we've designed a textile triboelectric harvester that has two triboelectric materials, so a positive and a negative, PVC fabric and nylon fabric. And this slides backwards and forwards along this silver electrode. And as it slides, you basically get a charge being transferred from the positive to the negative material, and that builds up an electric field, and you get voltage pulses as it moves across these electrodes. And by having both positive and negative materials, you get a positive negative voltages that combine to double the amplitude of the output. We can see it working in this video, which just shows a researcher. Basically, he's got the generator on his sleeve, so as he moves, the arm moves against his body, and that generates electrical energy that powers the light. We look at that again, though, you can see he's moving his arm quite artificially. It doesn't help that he's standing on the spot while sort of running, but he's having to force his arm and move it in quite a deliberate direction to get that linear motion along the generator. So our next version was this sort of checkerboard design. So it has, in this case, a PTFE and nylon combination of fabrics. And the electrode is again in a checkerboard arrangement. And then in this case, the energy can be harvested from all directions. So as this material, the triboelectric materials move in any direction along the electrodes. So again, we can see this working here. So he's got the generator on one side on the sleeve and the electrode on the other side. And basically he's charging up a supercapacitor. And when there's enough voltage across the supercapacitor, it can power this simple electronic watch, which is a very simple little example of this working. But again, whilst it does work in any direction, you do have to maintain a certain amount of force. So to make this a practical solution, we've got to think about how this will be incorporated into a garment and how that motion will be coupled effectively between the two parts of the generator. And that's the sort of thing we're looking at the moment. Another version of a triboelectric generator involves electrospinning. Now, electrospinning produces very, very small fibers, typically around 1/100th of the size of human hair, around maybe a micron in diameter. You can make fabrics out of this, so non-woven type fabrics out of this process. It naturally comes off the electrospinning process, and you can collect it as a fiber mat. And what we've done is taken a PVDF, which is a standard negative triboelectric material, and enhanced its performance by adding PTFE, which has improved it's even more negative as a triboelectric material. And we've optimized the blend, the combination, so 20% PTFE to 80% PVDF by weight, and that produces the clearest increase in voltage output. So you can see here in the bottom left here, this is just the mode of operation of this particular example. So rather than sliding, this design just works in contact separation. So the materials come into contact vertically and then separate. And again, this lights up LEDs, etc., and produces very high voltages. So this is getting on for nearly 400 volts in total, but very low current. Another mechanical energy harvesting approach we've looked at is a topic, or is a device called a ferroelectret. So an electret is a well-known polymer material, typically polymer material, that is able to store charge at the surface. So it holds that charge for a very, very long period of time, indefinitely, depending on, if the conditions are right. And in a ferroelectret, basically we introduce voids within that polymer material such that the charge is stored across the surfaces of the voids. So each of these becomes an individual, the void becomes an individual electric field across it. And if you apply a force and these voids change shape, you change the electric field accordingly, and you get a net flow of charge, a net voltage output. So they look just like a sort of piezoelectric material. If you squash it, you get charge output and you get a voltage signal, etc. But the mechanism is very different to piezoelectricity. So from a wearables point of view and from a textiles point of view, we want to work with very flexible, soft materials. So initially we did a lot of work on PDMS as the material for this, and we micro-engineered deliberate structures with precisely controlled voids. And then we can predict exactly how this material would behave. But PDMS isn't the greatest electret material. It doesn't store charge particularly well, particularly stably. So again, we added PTFE, which is a very good electret material. We added that in a powder form to the PDMS, and that improved the performance considerably. But one thing that did make it very difficult to make this structure relies on a bonding step. And if you add PTFE, you alter the surface energy of the PDMS and makes this bonding process very difficult. So our final sort of version of this was to go for a sort of a process where we deliberately induced bubbles within the formation of the PVDF PTFE blend. And these bubbles then act as the voids, etc. And we achieve that ferroelectret type performance. So that shows you sort of one with this ferroelectret process with a soft, flexible material. The other thing we did was actually come up with a process where we could turn any normal textile into a ferroelectret generator. So if we imagine that we've got an individual void here on the left, basically we can achieve this sort of effect by adding an electret material in a film form either side of a textile. And then we just simply have this bit here is just like an annulus. This actually prevents the charge leaking out, because this is an area where we kind of just infuse a polymer across the textile, as I say, to stop the charge leaking out. So we have our electrodes, our electret materials, and any textile can be sandwiched between these two electrodes. It's a very simple process where we basically charge up the surface of the electrodes, then bond them to a textile with that adhesive polymer annulus layer there for sealing and bonding them together. This again works very, very well. We get very significant or very high voltages, very high D33 coefficient. So this is a figure of merit for the sensitivity of the material. A typical piezoelectric material might have a D33 of, for example, 300 to 500. And with, for example, silk, if you have silk as the textile, we can have over a D33 of over 1,000. And this graph on the right here just shows a supercapacitor being charged up by the ferroelectret generator. So again, this can turn any textile into either a sensor or an energy harvesting device with this process. Another form of energizing or powering the textile is to use wireless power transfer techniques. So I think we're all familiar with the electric toothbrush that you put on a cradle and it wirelessly recharges the toothbrush. So we can use the same sort of principle with textile devices. And what we actually do here is use something called resonant wireless power transfer. So we operate the coils at a resonant frequency. So they're tuned and they match each other. And that vastly improves the efficiency of that wireless power transfer and increases the range over which you can transfer the energy. We are, however, constrained by the fact that the coil needs to be fabricated on the textile. And that produces constraints on the performance of the coil. So we've looked at a variety of ways of doing this. So screen printing, silver coils, we've embroidered coils with a conductive thread. And what we found that the best way to do it is another embroidery process where you take a Litz wire, a multi-strand copper wire, and you basically overstitch that, in this case, in this geometry here, a round coil. You embroider that onto the surface of the textile. And this produces the highest performance textile coils that we can achieve. So this works very well. This is, it can transfer lots of power. I'll show that in a moment. But to overcome the fact that the textile coils aren't as good as other coil types, for example, like PCB coils, they're better. We've looked at ways of, or systems, wireless power transfer systems that basically further improve and offset the disadvantage of the coils. So by separating the coils that are involved in the wireless power transfer, if you separate those from the source and the load, you can actually improve the efficiency. And more importantly, you improve the tolerance to misalignments, as we can see. So there's a lateral misalignment here, and there's an angular misalignment shown in the bottom left here. And these graphs just show the four coil performs best under both these conditions. And so for practical applications, this arrangement, this four coil arrangement, is definitely preferred. And when we always talk about energy harvesting, people always think, can I recharge my mobile phone, for example? Well, with this technology, you can. So we have a demonstrator here where if you sit in a chair, the chair has an array of coils. And if we have a jacket that people wear, and you can literally put your phone in the jacket pocket, and the energy is transferred from the chair and will recharge your phone whilst you're sat in the chair. So that's points to a sort of potential application for the technology and shows how much power can be transferred. It's watts of power under the right conditions, and that's perfectly safely. Just further illustrates the amount of power that can be transferred. We did this example here where we had a screen printed coil. We went back to screen printing for this one because we were able to embed one of the tuning capacitors actually in the structure of the coil. So there's a double layer, conductive layer in part of the coil, and by controlling the length of that, it acts as a capacitor which is involved in the tuning circuit. And we use this to power this heater. So I guess the example scenario here is you're sat in the chair with the coils providing power. And in this case, that received power, rather than charging your phone, is used to directly heat a heater within the clothing. So you could, rather than heat the whole room with central heating on a cold winter's day, you could simply heat your clothing, which is a much more energy efficient way of staying warm. And again, this produces watts of power under the right conditions. Other wireless techniques we've looked at. So the resonant approach works in what we call the near field. So it'll, depending on the size of the coil, it'll work over tens of centimeters, no more than sort of 20, 30 centimeters. But we can use RF technologies to transfer power over much longer distances. We've looked at a variety of textile antenna designs, rectifier designs, etc. This is just one on the left here, one example showing a SWIPT antenna, so simultaneous wireless information and power transfer. So it's basically one antenna design that does both wireless power transfer as well as communicating data. So if you look at the antenna design here, there's one part of it which is used for the communications at 2.4 gigahertz, and then the outer part is used for the wireless power transfer, and that has a very broad band, so it's not very directional, whereas the communications aspect is quite directional and it has a higher antenna gain. But so there's lots of clever things you can do with the antenna design. You have to be very conscious of the fact this is going on the human body, so the human body will influence the performance of the antenna. But if you design everything correctly, then you can achieve very reasonable levels of power transfer, and over ranges of several meters, you can transfer enough energy to power your e-textile electronics. And finally, on the right-hand side here, it just shows an example where we've combined the two approaches. So we have a coil for near-field wireless power transfer, and in the middle, we have another two antenna designs here for the wireless RF wireless power transfer. So this works both in the near field over 10, 20 centimeters, transferring lots of power, and further with the RF aspect as well. So I've spoken about harvesting or transferring power wirelessly. There are, the whole motivation for this is removing the reliance on traditional rigid batteries. But if we do want to store some of that energy, then we do need a reservoir within the textile itself. And textiles have already been used. So, for example, carbon-coated textiles are already used in some conventional button cell batteries, for example. And that points to the fact that textile is a suitable material for use in batteries and supercapacitors. So we've done a lot of work over the last few years on turning the textile into an energy storage device. So in this slide, I'm going to just introduce some work on supercapacitors. So on the left here was our first example device where a supercapacitor is basically like a conventional capacitor with two electrodes, but the electrodes are made from special carbon materials that have a very large surface area. So they're a porous carbon material. In this case, it's called activated carbon, which is a very low cost, widely available carbon material. And we simply spray coat this onto the textile. And by controlling how we spray coat it, we leave a region of the textile in the middle uncoated. And this acts as the separator between the two electrodes. And then you simply add your electrolyte and you have a very well-performing supercapacitor with excellent cycling stability. So this graph just shows the first cycle and the supercapacitor performance after 15,000 cycles. So it's very, very stable. This process on the left obviously worked, but you do have to control that coating process. And it's very difficult to do for certain textiles, very thin textiles or textiles that wick and transport that electrode very, very rapidly. So we developed a process for adding a porous membrane within the textile. So this is just SEM, just shows the porosity in the membrane, and this just improves the separating performance of the textile. And with this porous membrane, we can turn any textile into a supercapacitor. So you first deposit the porous membrane, you make the membrane, and then you add your electrodes, which sit on top of the textile. And then we just show, this just shows an exploded view of the current collectors and the encapsulation process, which I'll show in a moment. And again, this works very well, has a similar sort of cycling stability, and is very mechanically robust. So that just shows after we can bend, etc., twist, mechanically deform the device, and it works. It still works very well. We've done a lot of things to try and improve the supercapacitor performance, such as adding Maxine materials, for example, and that does have a significant improvement. So that improves or reduces the reduces the resistance, internal resistance of the carbon electrodes, just by adding a very small percentage of Maxine to the supercapacitor. So I mentioned about the encapsulation. So the challenge really with this technology is how do you transfer this device onto a textile, onto a garment in a reliable way. So we have to use an electrolyte that's like a solid electrolyte. So, aqueous electrolytes are not very practical. And we have to combine that with the current collectors. The current collectors, the challenge we have is that typically the current collectors react with the electrolyte during the charge transfer process. And the current collectors very quickly deteriorate and affect the performance of the device. So we've come up with a way of protecting or isolating the current collector, which in this case is a thin copper film. We isolate that from the electrolyte using a very thin carbon layer. And then we add that to an EVA film and seal that either side of the textile device. This is our very first sort of foray into this encapsulation. These are quite recent results. It's looking very promising, but we do have to improve, reduce the thickness of the encapsulation, etc. So there's lots of optimization to do, but we are working towards this practical supercapacitor device on the textile. So we can also take exactly the same sort of process where we have the porous membrane, but instead of having carbon electrodes, we can just simply change that to make it a battery by adding, for example, zinc electrodes and magnesium dioxide electrodes to make a simple zinc-ion battery. And we did this a while ago with our first sort of attempt. It worked, but not a great battery. So we've spent a lot of time trying to optimize the performance. So, for example, using Mn3O4 rather than the manganese dioxide, and that produces a big improvement in the battery performance. We've also done a lot of work on things like water-activated batteries. So these are single-use batteries that can remain dormant, sit on a shelf for a long time, but when you want to use them, you simply add water and they activate and produce power. So these, for example, are used in emergency power supplies, such as life rafts, for example, in ships and on airplanes. If you come into the contact with the water, it automatically, the battery comes to life and automatically will light the beacon and power the sort of rescue type devices. So there's a sort of simple application for that, and we can embed that in the textile. And one thing we've done, another thing we've done is by combining the supercapacitors with the battery. So very interestingly, you might think batteries have a much higher energy density than the supercapacitor, but the supercapacitor has a higher power density. And by combining these in the right ratio, you can actually improve the performance per unit area, surface area, quite considerably. So this just shows we take a supercapacitor and battery of exactly the same size, and we can make these on the same textile. And by combining them correctly, we can achieve a large increase in the capacity. So rather than having lots and lots of batteries, you add a few supercapacitors with them, connect them in the right way in series and in parallel, and you can improve both your energy and power density much more than you would if you just have the battery alone, for example, for the same surface area. So that's a very interesting result and something, again, we're taking further. And of course, we can combine the energy storage, the batteries, with the energy harvesting or the wireless power transfer. So this is just an example here where we've combined the textile supercapacitors. So we've got 3 supercapacitors connected in series, so we can get up to 3.6 volts. And these are very effectively recharged or charged up with an RF antenna and rectifier here. And basically this works very well. It's just an example of how the textile energy storage can be charged up wirelessly using RF power. So that's all the energy side sort of covered. So what I'm going to move on to now is how we actually make electronics into the textile, the various technologies and processes we've developed. The first example here is what we call a flexible filament circuit. It's a very simple example of a flexible electronic circuit. But what we do, which is novel, is we take bare electronic chips, die, so run not the packaged die format, the bare die, and we make it in a very thin, long, thin format, such that if these chips are small enough, we can actually put the circuit inside a yarn. If the chips are a little too big for that, so the width of this flexible filament circuit will be governed by the size of the die. If it is too large to put inside a yarn, this form factor is still ideal for weaving into a textile or putting in the seam of a textile. But basically, the other novelty here is how we package the electronics in such a way that they can survive, for example, machine washing. So reliability of the circuit is key. And this has been very carefully designed to maximize the longevity and the reliability of the circuit. So we'll just show very quickly, just show an example of how this circuit is, in this case, this is being woven into a textile. So the circuit, you can just see being manually positioned inside the textile. This is obviously a manual weaving process. A very simple circuit here with a little LED, just so you can see where the circuit is. And by building the textile around the circuit, you actually add further protection from the textile. It improves the reliability of the circuits. And if your components are small enough, I can promise you cannot find the circuit in the textile. You won't be able to feel it. They're almost invisible. But this is a manual weaving process, so we're looking obviously towards scaling this up towards mass production. So the circuits have to survive automated weaving. So this is just an example of a circuit being attached to a carrier yarn, and this will be fired into the textile as it sort of weaves this textile. So it goes off, as you can see, it goes off very fast. It's a very physical process, and obviously these electronic circuits have to survive this, which they do. So we have our own weaving machine, automated weaving machine. We evaluate all these sorts of things on. And this is an example here of just a large piece of textile where we're evaluating the reliability of the process. So we had 100% yield, so all the circuits survive that weaving process. One thing I would say, though, the electrical connections is very challenging. And this highlights the challenges of making, basically, what do you do with the wires? So each circuit has a wire that needs to be attached to the power supply. We've got the power supply rails in the warp direction on the textile, but essentially these little wires for each circuit have to come out and be soldered to each of these wires, and that's a manual process. It's not very aesthetic, it's not very good to look at, and it's not practical. So again, this points to the challenges around wiring and how we do this in a cost-effective and reliable way. I'll come back to that again, a bit more about wiring in a minute. The other manufacturing process we've developed for our e-textiles, and this is a way of depositing smart materials onto the surface of the textile, is to use basically standard printing techniques, such as screen printing and inkjet printing. And these are widely used in the electronics industry for making hybrid circuits, and also in the textile industry for patterning the textiles. So we have a nice professional electronically controlled screen printer we use, so we can reliably print the functional material. So this just shows a little an example of the functional ink being printed onto the textile. It's simply dried and in this case thermally cured, and we attach our textiles to a rigid substrate just for that printing process. The other printing process we use is a dispenser printing process here, where the same sort of ink is basically placed inside a pneumatically driven syringe, and you can print any design directly from the PC onto the textile. So the screen printing relies on a screen which has to be designed and sent off and manufactured, etc. This case, we can go directly from that design straight onto the textile. This is just showing an example of an electroluminescent. So by building up the printed layers, you can build up a device, etc. The downside of this process is it is a little bit slow. So it's great for prototyping, but you wouldn't use it for mass production. And this just finally shows the electroluminescent device lighting up. Other things we do is spray coating as well. So for large areas, we spray coat. Inkjet printing, we do a bit, but the inks the rheology requirements for the inks are quite difficult. You can't get too much, you can't load them up with lots of particles, for example. So we use inkjet printing probably the least out of the printing processes. Just to give us an idea of some of the inks we've developed. So we have developed an interface ink that you coat the surface of the textile. So you have to do this to make a nice smooth textile surface. Otherwise, you've got a very fluffy, rough surface to print on, and that's very, very challenging. Other layers, encapsulating layers as well, basic functional layers, conductive inks, dielectric inks, electrode inks that are designed to interface with the skin for ECG, for example, monitoring, and then more advanced functional inks, so piezoresistive strain sensing inks, piezoelectric, as we saw, electroluminescent, and even semiconducting inks. So we can print transistors now onto textiles. Another thing I've just introduced, so this is something we did a couple of years ago, which is proving we're developing this quite a lot at the moment. It's basically a yarn coating machine where we take the same inks and we put the inks in a syringe, and you draw a yarn through the syringe. And by controlling the speed of that process and the size of the yarn, it produces a very nicely controlled yarn coating process. So this is our very first, a very early machine. And you can see the ink coming out of the nozzle. This literally worked on day one. We built the machine, turned it on. It worked first time. And it does produce very reliable, very precisely controlled coatings. And you can build up layers, etc. And for example, you can build up this electroluminescent yarn here. And you can just see a cross-section of a yarn. We can have, in this case, a steel core. You can have copper. You can have traditional textile yarns, etc. It works with all types of yarns and wires. Very quickly, I'll just show this. This is a reverse offset printer we've developed. And the attraction to this is basically it's very high resolution. So it basically uses a process where you coat. This video is just showing the electroluminescent structure. So to demonstrate it, we're just going to show some printed electroluminescent pixels. And the advantage is you can achieve much higher resolutions. So this shows a typical screen printed array compared to the reverse offset printed array. So it's the same number of pixels, but much higher resolution. So I must apologize, the quality of this video is not great. Basically, this roller will roll across, it's coated in ink, the roller, and it rolls across a cleche. This is the cleche here, which is a micro machined silicon wafer. And the ink is transferred from the roller onto the cleche, except where the patterns have been etched. So some ink will remain on the surface, of the roller, and that pattern will be then transferred to the substrate, which is on the next stage. So basically, you get the negative image of the device you want to print on the cleche, and then you get the positive image deposited onto the substrate. And again, you can build up layers, etc. You line them, etc., and you can build up the pixel array and achieve much smaller pixel sizes. So that's a way of achieving higher resolution. We can reliably print down to sort of 30 microns with this technique. Something we've got, which I'm very excited about, this is coming in a couple of weeks' time, is a capillary printer. So this is a bit like those dispenser printers I mentioned, but it uses capillary action to eject the ink from a nozzle onto the substrate. And the attraction to this process is it can go down to 300 nanometers. So now we've got the possibility here with this technology to make very, very small printed electronics onto textiles, etc. So that's just an animation showing how it works in theory. Like I say, we yet to receive the machine, but once we've got the ink sorted, etc., I'm looking forward to using this. Right. I'll just very quickly say that we've got the two technologies. We've got the flexible filament circuits. We've got the printed materials and printed smart materials, etc. There's obviously an issue, a challenge around how you connect these two together. So we spent a lot of time looking at various ways of electrically connecting them. It is really challenging to do it reliably. So we've looked at anisotropic adhesives, etc., mechanical soldered fixings and things like this. Another example here is a device where we're actually combining electronics here in an ECG, so for monitoring the heart. And again, we have to make the electrical connections for each of the circuits to in this case, these are transfer printed interconnects. And again, they're very challenging to make this practical. So in the end, we basically used textile ribbons with conductive wires and soldered the connectors on. This was the most reliable solution. And basically, just highlight this, mention this is really challenging to actually implement the technology in a garment for a practical application. But I will show in a moment it does work. When I introduced the filament circuits, I mentioned about the packaging process. So this has been patented now. And we basically use a vacuum forming process. I'll start the video in the interest of time. This will illustrate how washable the circuits are. So these circuits just have a simple RFID tag, which has been encapsulated using this vacuum process. So you basically put your circuit in the encapsulation machine, you heat up a polymer film, and the vacuum sucks it down over the circuit. and it basically seals all the devices, etc. Even large chips like this or large devices like this, it conforms very nicely to the electronics. It obviously keeps water out, but it also adds mechanical reinforcement to the components, which makes them more reliable. And this is just in the, as you can see, the circuits are, the tags are going around the washing process. You can actually read the tags while they're being washed. And circuits can survive typically, depending on the nature of the circuit, they can survive 50 washes before they start to fail. Now, just some examples. So this is an example of integrating the filament circuits, in this case, into a textile mat. So this actually was a student project with a local company that make the textile mats, and they wanted to explore the adding electronic functionality to that. So we added flexible filament circuits to the outside edge of the textile, and then we put the GPS sensing electronics and power supplies in a separate module here. So this is wirelessly powered. There's a coil on the map. But basically, this basically tells you where you are on the map. So the GPS electronics identifies the position. This is converted into depending on where you are, the nature of the map, the location. And by lighting up, you can tell where you are on the map. And then there's a key for higher resolution. So it gets to you to within about 50 meters on the position of the map. And it can tell you when you're off the map and things like this. So that was a nice little example. We're doing a lot of work on wireless devices, so trying to remove the reliance on batteries. So this is an example of a capacitive, sorry, not a capacitive, an RF powered breathing sensor. So simply by looking at the response of the antenna when it's located on the chest, as you breathe in and out, you change the dielectric properties of the body changes, and that affects the antenna performance. So this gives an example of monitoring someone's breathing wirelessly. There's no batteries involved, actually no electronics involved. You've just got to monitor the performance, the behavior of the antenna. So it points to the feasibility of this as a sensing mechanism. In this case, you obviously need to connect your antenna. Here, in this case, it's a vector network analyzer, so that's not a practical solution, but it just indicates that it works in principle. And we have now got some demonstrators that work without the VNA being required. So the electronics is powered by the RF. The whole system's powered by the RF, and we can monitor breathing using sort of RFID type technologies. I showed this earlier. This is a 5-lead ECG vest, and we came up with this wiring interconnect solution. And this just shows, this is the electronics that goes with that device integrated within this shirt. And this just shows basically the route someone took around the university campus, monitoring the heartbeat. And the challenge, we ran out of time with this project, but to really finish it nicely, but it did work, but you do get motion artifacts. So I think this is when you're going upstairs, for example, the electrodes move against the skin and you lose the signal. But once you're walking normally, the signal comes back, etc. So it did show that we did actually achieve a nice working 5-lead ECG system, but we do have to remove the motion artifacts. That's just the final version of the system. Some other examples we've done. So with the flexible filament circuits, we've done a wirelessly powered smart bandage. So this bandage monitors a wound, so the temperature, for example, of the wound, but also very importantly, this can actually illuminate the wound with UV light, and UV light will kill bacteria and viruses. So if you've got a persistent wound that's not healing and is infected, then the UV light will actually treat the infection. So you can deal with persistent wounds without relying on antibiotics, etc. So that's all powered with inductive wireless power transfer. So there's no batteries on the bandages at all. Another example sensor here is an IDT electrode structure that's attached to an armband, and this is used to monitor atopic dermatitis, which is an itchy skin condition, quite unpleasant for people who suffer from it. These have been designed specifically such that the electric field is concentrated in the top surface of the skin, and he basically looks at the dielectric properties of the skin. If you've got a region where you've got atopic dermatitis, then the dielectric properties are different. And you can use this sensor to see how bad the atopic dermatitis actually is. So, and it's obviously wearable. It's something the patient can use themselves. So we're developing this further with the local hospital. And the last slide is basically some other wireless sensors. So again, looking at getting rid of wires and using wireless techniques to both power the electronics and do the sensing. So this just shows an example where you have RFID type tags where one is coupled to a sensing element, and resistive or capacitive type sensors will work with the technology, and the other is not coupled to the sensing element. And by looking at the differential response of these two elements, you can get a measure of whatever it is you're sensing. And the other thing we can do is add the antenna to a material such that the dielectric properties of the material change with whatever it is you're measuring. So in this case, we've added an antenna to a thermo composite material that changes its dielectric properties with temperature. And simply using an RFID reader, you can wirelessly measure temperature over the sort of up to 65 degrees. It works very, very nicely. So no electronics and no battery needed. So that's it for this talk. Thank you for your attention, and I'll welcome any questions.
Thank you, Steve. Thank you for your presentation. Yes, now session is open for question. You can speak up or raise your hand, or if you would like to write on chat box.
May I ask a question?
Sure.
Firstly, thanks for the presentation. It was very helpful. I'm wondering, as material, is it applicable for artificial leather?
Sorry, can you say that again?
As material, is it applicable for artificial leather?
So artificial. I didn't catch the last word. I'm still not. Do you think you could put it in the chat? Sorry.
Okay.
Oh, artificial leather. Sorry. Yeah. So certainly the printed materials we've developed, they're all developed in such a way that they are thermally cured at low temperature. So absolutely would be used compatible with artificial leather. Yeah.
And I have one more question.
Yep.
I can write it in chat box.
Yeah, that's a really good question. So it's hard to, so the demand for the product. So at the moment you can buy e-textile garments, but they have very limited functionality. There'll typically be 2 electrodes for monitoring the heart rate, for example. There are some that provide electrical stimulation for helping rehabilitation and things like this. But yeah, they're basically quite limited and they're quite expensive. I think if we are looking again, there are so many potential applications. So if you're looking at military applications, so the smart soldier, medical applications, the smart bandage, etc. So again, textiles aren't just used in clothing; they're used in soft furnishings. They're all around us. We're sat on a textile-coated chair. Inside the car interior, there are textiles. So I think and if you add the ability to add the smart functionality to the textile. I think there's a vast range of opportunities there for this technology. I can't exactly say, but if you look at the market studies and people who looked at the textiles, they expect this area to grow very rapidly, and certainly academically, the numbers of papers being published in the area is growing considerably, growing very rapidly as well. Sorry,
its ranges high and it's expensive. You mean, I get it right?
So say again.
There's a range product and it's expensive, you know.
At the moment, the products are expensive, yeah, because they're typically manually made. A lot of the processing is manual. So which, again, looking at processes, assembly processes that aren't manual is a key thing for bringing down the technology. And if you can remove wires, that you go a long way towards making it much cheaper to manufacture. It's that wiring process which is a nightmare.
Thank you very much.
Thank you. So we can use natural fibers as well for sustainability. Yeah, absolutely. So yeah, we work here with organic cotton textiles as our substrate. So sustainability is certainly an issue, and we do have to think about how we separate the electronics from the textile at end of life. So that's a big consideration in how we think about assembling the devices. The most important thing to do is make the electronics as reliable as possible, so they last as long as possible and can potentially be reused. But when you do have to finally discard the garment or whatever it is, you have to be able to separate the two waste streams. What are current challenges for wireless sensing and related future work? Yeah, the requirements for wireless sensing. So it's at that stage where everything works nicely in the laboratory, but you have to get it into the real world. And things like RF, the performance, the range, for example, will change depending upon the environment and how much noise is present in the environment and things like this. So it's really about making the things robust and work in a wide range of environments. I'd say that's the kind of like the biggest challenge. The RF technology, for example, is relatively low power as well. So you have to make your electronics that receives the power functional low power, low energy levels. So you've got to be very careful about your electronics design. Have you done any of these technologies in home textiles yet, such as terry towels? Yeah, well, the RFID demonstrated with the washing machine was on towels. We actually haven't really done any home textiles yet, not soft furnishings, other than putting the coil into a chair for the wireless power transfer. That's probably the only thing we've actually done for home textiles, yeah. The sensor that senses breath. Yes, okay. So basically that is a simple antenna. It's interrogated by a wireless signal that's transmitted, and then that reflects the signal back. So it's an RFID type technology, and you can have an RFID tag attached to the antenna, and that you can buy RFID chips now that will actually take a sensing input, so a capacitive sensor. So you could have a capacitive breathing sensor attached to your RFID tag, and as you breathe, the capacitance changes, and that modulates the reflected RFID signal, and you basically just pick that up on the RFID reader. So that's how the latest version of that sensor is working. I've used acrylic and cotton for tribo. Yeah. Yeah, the reason we've used those materials that we highlighted is that they're at the extremes of the triboelectric scale, so they produce the biggest voltages. But absolutely, you can use different materials. Yeah. Do I think energy harvesting technologies can be adopted to pacemakers in medical? Potentially, yes. Pacemakers are very low power devices. Do we really need to do that? The pacemakers, well, the batteries last for a very long time nowadays. I think, yeah, it could be done. I think they produce enough energy for that. But whether there's actually a need for it, given how the batteries work in that application nowadays, I don't know. You've got a challenge about getting the harvested energy to the pacemaker. So yeah, that would be a challenge. But yeah, in terms of energy, I think that's compatible. So that's all the questions from the chat. So
thank you for your for great presentation and your participation.
I have a question as well.
Yeah, hocam, yes.
Hi, Steve.
Hi there. Hi again.
The AFM cantilever, the printing is very interesting though. So just I am wondering if you just coat, the surface of cantilever with the ink, so whether it will engage to the surface or not. So does it break, the engagement of that cantilever to the surface?
So are you talking about the new printer we've got coming?
Yeah, AFM assisted,
Well, so the AFM part really refers to the positioning of the nozzle. There is no AFM probe in that, so they replace the cantilever with the nozzle, but they use the AFM positioning accuracy. I see. Yeah, there's no cantilever, so there's a little glass capillary nozzle that ejects the ink onto the substrate. So that's instead of the cantilever. So yeah, it's inspired. It uses the AFM sort of bed, if you like, but there's no AFM probe. Yeah.
All right, that's great. Thanks a lot, Steve.
Okay.
Is there any question? More
May I ask the last question?
Yes.
Yeah. Okay. Hi, Steve. Thank
Hiya.
you for talk, and we appreciate your contribution. And I have a question about the output power of the energy harvesting from the flexible textile. Is it possible to enhance the power by scalability and also deployment over the large surface like sail, or using some kind of the cover of the building or something? I'm just wondering the limit of the harvesting energy from the textile. Is it compatible? For example, power per square, is it compatible with the solar energy?
Yeah. So okay. So in simple answers, depends on the technology. So people have put solar cells on the surface of textiles, and they've embedded silicon solar cells inside the textile. Things like antennas for RF, etc. These technologies will scale with surface area. So the larger the surface area, the more power you can get. So the larger the antenna, then the more power you'll get, for example. Things like mechanical energy harvesters, that's more difficult because that's very application dependent. It depends how the textile moves. But yeah, for some technologies, absolutely, the area will help you. Indeed, the energy storage as well. So it doesn't matter if the textile battery isn't the best battery. You can simply make it bigger because you've got a large area. So you can increase the energy capacity. So yeah, it does. The large area can help you. Yeah.
Oh, thank you.
Thank you.
Steve, thank you for your presentation. And
That was a pleasure.
thank you all participants for your participation. It was a great webinar. Thank you for your time and effort.
Thank you for the invitation and nice to talk to you.
Thank you. Have a
Thank
good
you.
day.
Thank you. Bye-bye.
Bye.
Bye.